Hi, today we're going to be talking about formal charges, and we'll also talk a little bit about functional groups. So when we look at formal charges, this is a way to keep track of how many electrons are found or not found on a given organic molecule. So if, for example, we look at this molecule here, this is isopropanol from before. And we have some sort of reaction arrow here going to a compound now that is lacking this proton or this hydrogen atom. So the question is, what's gone on here and how do we represent this? It's important to recognize that this molecule here is not the same as acetone over to the right. You can see that there is not a double bond, and so something is clearly missing. What's missing are drawing in the hydrogen atoms. We always have to keep track of the fact that when we have this type of line structure, there is a implied hydrogen atom drawn in here. So sometimes it's handy to draw this in. It's also important to recognize that there are electrons involved on this oxygen atom, and in this case, this reaction has involved the loss of a proton, and the resulting compound now has a negative charge. And so today we're going to talk about how do we calculate this formal charge. And so the formal charge calculation, it's formulaic. What you do is you take the valence electrons of a given element, and you get that from the periodic table. So oxygen has 6. Then you subtract the number of shared or bonded electrons from that. In this case, there are 2 bonds. I've highlighted in blue here, 2 bonds, so we subtract 2. And then you subtract the number of electrons that are found in lone pairs. So in this case, there are 4 electrons found in lone pairs, 1, 2, 3, 4. And so if you add this all together, 6 minus 2 minus 4 equals 0. So the math in this class and certainly in this section is all relatively simple. So if we now look at the compound up here on the right, how did we calculate that -1 formal charge? Well, again, you start with 6. That's because it's oxygen. You subtract 1 because there's 1 bond to it now. We've lost that bond to the proton. And then we subtract 6 because there are 6 lone pairs of electrons, or 6 electrons that are in lone pairs. So there's 3 pairs of electrons. And that ends up equaling -1. So we draw on our negative charge on that anion. So let's look now, instead of removing a proton, let's see what happens when we add a proton. So now isopropanol, let's say you interact isopropanol with a strong acid. We'll talk about acids and bases later. Sometimes people will say, oh, you can't have this many bonds to oxygen. That's untrue. You can have this many bonds to oxygen, but you have to take account of it. It's not necessarily stable, but it is possible. So the formal charge, we find the valence electrons. So there's 6 valence electrons. In this case, we have 3 shared bonds to oxygen, 1, 2, 3, and we only have 2 electrons that are found as a lone pair of electrons, so that gives us a total of a positive formal charge on this oxygen atom. It's important to actually recognize that the formal charge does not mean the charge is actually on the oxygen atom, but it's actually shared and delocalized across the molecule or across atoms that are bound to oxygen. So in reality, the positive charge would be more likely found on the carbon and the hydrogen atoms. They are more electropositive than oxygen. But we draw the formal charge on the atom or heteroatom to just keep track of charges. We'll talk more about that once we get to reactivity. So let's do some practice with formal charges, and let's look at it in the context of carbon. It's a really common element that we work with. So the first molecule we're going to look at, carbon, again, there are 4 electrons in neutral carbon. In this case, with methane, you have 4 bonds to hydrogen atoms here. There are no lone pairs of electrons, so 4 minus 4 minus 0 equals 0. In this case, we have a carbonyl, and how do we deal with the double bond? Well, the double bond is another pair of shared electrons between the atoms. So there's 1, 2, 3, 4 bonds to this carbon. And again, there are 0 lone pairs of electrons on that carbon atom, and so therefore, again, the formal charge is 0, so we don't draw anything on there. In the next case, we have, again, carbon has 4. We subtract 3 from that because there are 3 bonds to hydrogen atoms. There are no lone pairs of electrons drawn here, and so it ends up having a positive 1 formal charge. So we draw a positive on there. And the final molecule to the far right, you have 4 because it's carbon, minus 3, 3 bonds, minus 2, 2 lone pair, 2 unpaired electrons, and you end up with a formal charge of -1. So we call that a carbanion. The next element we'll look at quickly is nitrogen. And I'd say you can practice this with lots of different elements. Nitrogen, so this compound on the far left, you have nitrogen, which has 5 electrons on it, as we've talked about before. You have 3 bonds to nitrogen and 1 lone pair of electrons. So 5 minus 3 minus 2 equals 0. So it's neutral. So that's ammonia. Now, if you add a proton to ammonia, so ammonia is a base, if it reacts with an acid, it gets protonated. And so you have 5, again, because it's nitrogen, minus 4 bonds now. There are no more lone pairs of electrons, and so it's 0, and you have a formal charge of +1. And so you draw that positive in. And the final compound on the far right, and so that compound in the middle, we call that an ammonium ion. On the far right, we have a nitrogen, so 5. There are 2 bonds to it. There are 4 electrons in lone pairs, and so you end up with a -1 charge, and that is an amide anion. So I'm going to take we're going to move away from formal charges. Formal charges, again, is something that you should practice and work on with your study groups and on your own. We're going to talk about functional groups and do a little bit, this will be a portion of the video where it will be just kind of information flying at you. And here's some really important functional groups that are worthwhile putting on study cards and learning. So the 3 that we learned from a few videos ago, alcohol, amine, and ketone, are really important to know. But also, let's look at some other ones. So if you have, so a ketone is a carbonyl when you have carbons on both sides. If you now have a nitrogen on one side and a carbon on the other, we call that an amide, or an amide, but I often call it an amide with my accent. If you replace that nitrogen with an OH, that is now called a carboxylic acid. And here we have acetic acid drawn here. This is what you have in vinegar. If you have an oxygen with 2 carbons on each side, so in the case of an alcohol, you have 1 carbon and 1 hydrogen. In this case, you have an ether, so you have a carbon on one side, 2 carbons on each side, and an oxygen. If you effectively mix a carboxylic acid with an ether, so that this oxygen it no longer has a proton on it, this is called an ester. If you, instead of having 2 carbons on the carbonyl, you have a carbon, and a hydrogen, that's called an aldehyde. If you now replace the oxygen atom with a nitrogen, that's called an imine. If you protonate that imine, it's called an iminium, but we don't have to look at that right now. If you replace the carbon on the side of an amide with a nitrogen, so now you have 2 nitrogens and a carbonyl, that's called a urea functional group. If you replace that oxygen with a nitrogen, that is now a guanidine. And to wrap up this whole thing, if you replace the oxygen with a sulfur, it's no longer an alcohol, it's now called a thiol. So one of the things I want to point out here is that these are all important functional groups in the context of biochemistry and in the context of really all organic chemistry as well. I want to highlight the fact that all of these compounds, these all have carbon double bound to either an oxygen or a nitrogen atom. And these all have reactivity and mechanisms that end up being pretty similar. So again, remember that functional groups are greater than the sum of the parts. And you can start to recognize trends in functional groups that will really help you when we get to the mechanistic portion of our class. Thank you for your time, and I look forward to seeing you again soon.